Okay, section 1.5, solving inequalities. We are going to start off with a review of interval notation. Interval notation, I mentioned it briefly in a previous section, but it's where you're going to use just two numbers in a little section. One of those numbers might be infinity or negative infinity, and it uses either parentheses or brackets, depending on whether it's a closed or open interval. So we'll look at just the notation up here, and then we'll move on to some examples down below. So an open interval is going to be like less than or greater than. When you put that on a number line, it's going to have an open circle on the number instead of a closed circle. And we use those for infinity all the time. So open intervals are going to have two numbers, both using parentheses. A closed interval would be for like less than equal to, greater than equal to, and we would use a closed dot on the number line, and we use square brackets for those grouping symbols. And then you can have half open intervals. So you might have a closed circle on one end and an open circle on the other, or it could be vice versa. Open circle on the left, closed circle on the right. Let's look at some examples going from interval notation. We're going to make that into inequality, and then also on a number line. So for this one right here, we have a half open interval, a closed circle on 0, and an open circle on 9. It's usually easiest for me to start with the, if I have interval notation, to go straight to the number line and draw it, and then make that into an inequality. So I've got closed circle on 0 and an open circle on 9. And then this in interval notation is telling me that everything between those two numbers is going to be shaded in. So I have that situation. When you have interval notation, one interval means we have one shaded area, and vice versa. If we have one shaded area, we'll have one interval. And then making this into inequality notation. When you use inequality notation, the letter X, or whatever variable you're using, represents the shaded part. And I can see in here that the shaded part is trapped in between 0 and 9. So I'm going to put my variable trapped in between 0 and 9. Then I use whichever symbol matches with the dot on my number line. Since this one is a closed circle, that is going to be one of these two symbols. Since this one is an open circle, that will be less than or greater than. When you have a compound inequality like this with a number stuck in two numbers on the ends and a variable in the middle, your inequality symbols always point to the left. So on the between 0 and x, I use the less than or equal to symbol. That's telling me that x is greater than or equal to 0 if I read it right to left. If I read it left to right, 0 is less than or equal to x. And then on the other end, x is less than 9. I also wanted to show you on my math lab, instead of using closed circles and open circles, they oftentimes will use square brackets and parentheses, which makes it a whole lot easier if they give you a number line and they ask you to make interval notation. I tend to do both, but you can see here that I used the parentheses and brackets. Okay, the second one, we're given an inequality and asked to do the number line and interval notation. So I've got the number 8 and x, which remember represents my shaded section, is going to be bigger than 8. Without the bar there, that means I've got an open circle or a parenthesis. So I'll use a parenthesis to be consistent with this problem. And then the shaded part is bigger than 8, so we go this direction. And then when I put that into interval notation, The first number I run across in my shaded section is 8, and it's got a parenthesis. And then it goes forever to the right. The arrows we read as either positive infinity or negative infinity. So this interval will go from 8 to infinity. Infinities always have parentheses. So we'll go ahead and close that off. Our third one, we're given the number line, and we have to make the inequality and the interval notation. When you have more than one shaded region, you're going to have more than one interval and more than one inequality. So if you have two shaded regions, these things always go together. Two shaded regions, two inequalities, and two intervals. So I'm going to use two separate inequalities here. The first one is going to go with this shaded region. So remember, x is the shaded part. So x is all the numbers that are smaller than -5. So the inequality I'll use will be x is less than -5. And I use the less than because there's a parenthesis here. And then I've got all the numbers bigger than or equal to 3. So x is greater than or equal to 3. Do y'all remember what we say in between those, what word we use when we have more than one inequality? This one is an or. So this is a picture of an or inequality. The one that we had up here, this is an and inequality, because my value x is bigger than 0 and smaller than 9 all at the same time. But in this one, there's no number that's smaller than -5 and bigger than 3, so that's why we use the or. Now when we're putting this in interval notation, again, remember we're going to do one interval for each shaded section, and each interval gets two numbers. This one starts at -infinity and ends at -5. This one starts at 3 and ends at positive infinity. So my first interval, I will start at -infinity, end at -5, and it's going to end with a parenthesis. My second interval starts at 3 with a bracket and ends at infinity. And then instead of writing the word or, when we have more than one interval, we use the symbol U for union, which means or. Set builder notation. So we've already looked at 3 ways to indicate the solution to an inequality: interval notation, inequality notation, and on a number line. Set builder notation is another way that you can give the solution to an inequality. And when you use set builder notation, it's really very similar to inequality notation. You're just going to do this curly brace and then the variable. This bar means such that, and then you give the rule for the variable. So in set builder notation, it goes curly brace, and then I'll read it to you left to right. So we go all values of x such that x is a real number or something like that. So we put the rule for x. So in this example, x is greater than 8. We would write that in set builder notation as all values of x such that x is greater than 8. It's really it's that easy. Oh my goodness, I'm so sorry. I was using the wrong finger there. Wow. My apologies. That was completely unintentional. But also peep that little thing. Okay, I'm doing it again. This is a Sharpie tattoo. Accidental. I stabbed myself with one of those really ultra fine Sharpies, like, I don't know, 10 years ago, maybe longer. Okay, let's go on to solving linear inequalities. We solved equations in a previous section, so now we're going to move on to inequalities, which is why we needed interval notation. With solving linear inequalities, now I'm specifying linear because there's a whole other set of guidelines for when you're solving nonlinear inequalities. And we'll get to that later. I don't think it's in this section. It might be. I don't know. We'll see. But if it's a nonlinear inequality, you got more work to do. If it's linear, you're just going to follow the regular equation solving steps, like add something to both sides, subtract something from both sides, multiply by something on both sides, divide by something on both sides. But there are two very specific things you have to watch out for that you're familiar with. And then there is another thing that I'm going to talk about you may not be familiar with. The thing you have to watch out for big time when you're solving inequalities is when you multiply or divide both sides by a negative number. Not just if you see a negative number in your problem, it's when you multiply or divide both sides by a negative number, you have to switch the sides. So you have to, not switch the sides, reverse the inequality. So if I had, let me give you an example here. Negative 5x is less than 35. If I divide both sides by negative 5, I have to switch the direction of the inequality when I do that. So in this case, I reverse because I divided both sides by negative. But if I had 3x is less than negative 21, like that, when I divide both sides by 3, even though I have a negative in my problem, I don't reverse. Because what I divided by was a positive number. Okay, so we have to reverse the inequality if we multiply or divide both sides by a negative number. Another time we have to reverse the inequality is if you switch sides. So in equations, it's totally okay to switch the sides. In inequalities, it's not totally okay to switch the sides. So if I had 8 is less than x, remember that x is the shaded part. So this is telling me the shaded part is bigger than 8. So if I switch the sides like that, the shaded part still has to be bigger than 8. So now I have to reverse the inequality. And it's going to go both directions. So I can switch either direction and that will still be the case. Let me see if I can find a Sharpie and quick. Oh, I have a dry erase marker. Okay. So I think about equations and inequalities like they're on a piece of paper. So if I had x equals 8, hopefully that's going through to the other side, versus x is less than 8. If I reverse this, see how x equals 8 stays the same, but the inequality reversed symbols. Here, I'll trace, or reverse directions. I'll trace it so you can see it better. Okay, so let me flip it back over. So when I reverse the sides, when I switch the sides, the equation is going to stay the same because it's an equal sign. It's like got symmetry. So when I flip it, it doesn't do anything. But this doesn't have vertical axis symmetry. So when I flip this around, this inequality symbol is going to be pointing the other direction. You ready? Here we go. It's like magic. So remember those 2 times to reverse the sides when you're solving inequalities. The third time that you reverse the inequality is when you are like, okay, I'll show you this. If you have 1 over a is greater than or equal to 1 over b, and I flip both sides over and make them a and b, I reverse that inequality. That only works when a and b have the same sign. I'll show you an example with numbers, and it'll make so much more sense. And I'll also show you when this is useful. Okay. So if I have, let's see, we all know that 2 is less than or equal to 8. I think we can all agree about that. Well, what happens if I flip those both upside down and I make them 1/2 and 1/8? What do you think? Is 1/2 bigger or smaller than 1/8? 1/2 is bigger than 1/8, so it makes sense to reverse that inequality. But why would I ever need to do that? If I am solving an equation like this, 1 over x is less than 3, I definitely could multiply both sides by x and then divide both sides by 3, and I will get the same correct answer. But I can also use this reverse the inequality trick and flip this side upside down and flip this side upside down and reverse my inequality and have a solution much faster. And there are actually times when only this property will work. Like you won't be able to solve it any other way. Okay, next property that you may or may not have ever heard of is the reciprocal property for inequalities. This might be new. I don't know. You'll have to tell me next time you see me. Reciprocal property for inequalities says that if a is greater than 0, then 1 over a is also greater than 0. And that goes back and forth together. So for example, if I have 1 over x plus 5 is greater than 0. Now, if I needed to solve this inequality, the legitimate only algebraic move we know is to multiply both sides by x plus 5. But what happens when I multiply the right side by x plus 5? 0 times x plus 5 will give me 0. When I multiply the left side by x plus 5, it simplifies down to 1. So then I have the true inequality that 1 is greater than 0. However, that's not super helpful for me to solve for x. So I use the reciprocal property. Wow, I can't spell. Reciprocal property. And I can flip it upside down. So if 1 over x plus 5 is greater than 0, then x plus 5 has to be greater than 0, which tells me x is greater than negative 5. Problem solved. And it works the other direction as well. If a is less than 0, excuse me, then 1 over a is also less than 0. Okay, let's look at a couple of examples. 1 over 3 is less than or equal to 1 over x plus 5. Now, we do have other algebraic methods to solve these, but this falls under that property up here, or not property, I guess, that guideline, I don't know, that if you flip over both sides, you reverse the inequality. So if I just flip over both of those, I will have 3, reverse that inequality, is greater than or equal to x plus 5. Subtract 5 from both sides. I have x, this symbol, negative 2. Now, if you want your variable to be on the left, I know a lot of you like that to happen. If I put my variable over here and my number over here, I have to remember to reverse that inequality at the same time. So this would be my inequality notation for the solution. If I put it on a number line, I'm going to go from negative 2 with a closed circle or a bracket. My shaded part is smaller than my negative 2, so to the left, to the left, to the left. Everything you own in a box to the left. Okay. And in interval notation, the two numbers The first one is negative infinity. The second one is negative 2. Infinities always get parentheses. This negative 2 gets a bracket because it has a closed circle. And then let's throw that set builder notation. So we go curly bracket, x bar. That bar means such that x is less than or equal to negative 2. Easy peasy. Okay, this one has fractions. Have we talked about the strategy that I use every time I see fractions in a problem? Well, not every time, but most every time. Almost every time I see a fraction, what I want to do is clear the fractions. And have I already talked about how to do that? I don't know. We'll write it down now. You're going to multiply each term by the LCD over 1. So this is a strategy we will use like a super bunch in college algebra and calculus if you go there. So we look at these. Our denominators are 3, 2, and 6. Hopefully you remember how to do LCD. If not, let's figure out a time that we can work together on that. We have an LCD of 6. So I'm going to multiply each term by 6 over 1, by 6 over 1, by 6 over 1. And then that's going to take care of all my fractions. How does it do that? Well, if I take 6 times 2, I get 12. 1 times 3 is 3. 12 over 3 simplifies to 4. And then I have minus 6 over 2. So 3x is greater than or equal to 6 over 1 times 1 over 6 is 1. And then plus 6x. Now that gives me a really super easy inequality to solve. If you prefer having all of your variables on the left side, we can do that. So we would have to subtract 6x. Well, that's really hard to see from both sides, which gives us negative 9x over here. And subtract 4, which gives us negative 3 here. But then we have an issue of dividing by a negative 9. Remember that when you divide both sides by a negative number, you have to reverse your inequality. So now we're going to have x is less than or equal to 1/3, which we could put in any of the notations. That's already inequality. We could throw it in some curly brackets and make it set builder. We could put it on a number line. We could put it in interval notation. My favorite way to do these is interval notation. That's probably because as you go further in math, interval notation is used a lot. So it's good to kind of get comfortable with it as we're going so that when you see it in the future, it's not scary. I think what I'm going to do is take a break from making videos, and I will make a second 1.5 video later.